putting your data into L1 and L2. And we have already done linear regressions this year, like back in November. But this final chapter of new material is going to be a review, or it's actually going to combine 3 previous concepts together. It's going to combine linear regressions together with the normal curve together with hypothesis tests. So 3 main concepts come together as one here. And because of that, then I need to make sure that you remember all the vocabulary and all the calculator steps that we have done for reviewing these regressions. So here we go. You've got your data into L1 and L2. And so you've got that there for this problem. And so let's talk about what's all about. We've got a sample of 10 Burger Bistro restaurants, and they are located near college campuses. So maybe around the central part of the country. They've got 10 college campuses, and they have their Burger Bistro next to it, and then they took a sample of 10. And they are wondering if there's a relationship between the student population, which is here, and these are in thousands of numbers, okay, so the students around that campus, and their quarterly sales. Now, why do you think in business that it might be important to see if there's a relationship between those kinds of things? If you're a business manager in this company, why might it be important to see if there's that kind of relationship? Perfect. So you can plan future sites. Because if you determine there's some kind of relationship there, then you can analyze that, make future plans for future businesses, and know if it's going to be valuable or not. It's going to be an asset or not. Okay, very good. So, we first want to start off with just some very basic answers. And so let's not get like way deep into things like residual plots yet. Let's first answer this. Do you think that there's a linear relationship between student population and quarterly sales? And what might be an indication as to why you think that? What could we do to visualize that? Okay, good. We can find the line of best fits. Why don't we just look at it first and see if it kind of looks linear? I mean, we're talking basic stuff here. So let's remember, how do I look at this data? Okay, turn on your stat plot, so go do that. Stat plot on. And I want to look at a scatter plot of L1 against, what's my y-list? L2, okay? And then how do I look at those statistics? Zoom 9, very good. Okay, now I actually have my equation in there already. Let me get that out. Okay, so there's your data. So does that give you an initial indication that there's something linear going on? It appears to be that way. Okay, so we can say that it appears linear from the graph. Okay, very good. So let's move on from there. The next thing is determine the regression equation for the data. So what process are we going to go through to get that equation for this line of best fits? Okay, good. Lin Reg. So you guys have already done that. So up here, and where are the buttons that you push for that? Stat. Calculate. And then you can choose number 4, or we also have in this class done number 8. So if I choose number 4, then which letter is going to be representing the slope? Good. Okay, here we go. A is 5, B is 60, and I do have my r squared and my r showing up. What are those called to get r squared and r to show up? Diagnostics. Good. If your diagnostics are not turned on, then you're not seeing that. To get your diagnostics on, do you remember where to go? Yeah, catalog, which is second 0, and find the letter D. I'm going to shortcut there. And then you got to go down a ways until you get to diagnostics on, and then you turn it on, and so on. Okay? So I skipped it, but it was the good thing. So diagnostics on, it's right there. Turn it on. And there it goes off again. Alright, so there's your diagnostics on, you got those on, and then you're able to come up with this equation. Okay, very good. So let's write our equation in context. So what do we come up with in context? This is going to be what? Good. So our quarterly sales equals 5 times the student population. Of course, these are in thousands, plus 60. And then there is something very important missing. This statement is too exact. This is saying every single point or every single observed piece of data is going to be 5x plus 60. Aha. If you put a hat over quarterly sales, then that's a prediction hat. So my predicted quarterly sales, that's saying this is not necessarily it exactly, but this is a ballpark prediction. Okay. Is the model a good fit for the data? Let's see. Let's go put 5x plus 60 into your equation and see how well that fits. Okay, so there it is. So what do you have to say about that? Does it appear as though the equation is a good model to fit this data? Yes, looks good. So is the model a good fit? Appears to be from the graph. Now, we have learned back in November some more statistical analysis to determine that. Namely, what other things might you want to reference to give that kind of a statement that a linear model seems appropriate? What kind of things might help with that? Good. R squared and R being 0.95 would mean what? Good. Good. There's a strong, what kind of, which direction? Positive, linear relationship between student population and quarterly sales. Good. So, again, R is that measure of linearity. Okay, R is that correlation coefficient, measure linearity. Now, D says interpret the slope of the regression line in context. This is something that, yes, it's from Algebra 1, but it's somehow you get stuck, and we can't make this real world connection. So I have 5x going on as my slope, or I have 5 happening as my slope. But in context of this problem, what does that actually mean? Close. Very close. He said for every 5,000 sales, 5,000 students, the predicted sales goes up by 1,000. Okay, so that's not entirely. So let's think about it. So if I make this student population 5,000 higher, if I make this 5,000 higher, is it going to make the quarterly sales go up by 1? That'd make the quarterly sales go up by 25,000. Okay, so let's fix that. You're very close. You started off perfectly. I like to start that off by saying for every. Okay, so that's a good start. Because it is. It's a reference between those two variables. So for every what? Good. For every 1,000 increase in student population. Okay, good. So every time this thing increases by 1, every time that goes up by 1, what will happen to the quarterly sales approximately? Good. Okay. So for every 1,000 increase in student population, the quarterly sales increase about, you can't straight up say they increase 5,000 because that is saying, yes, for every 1 increase, it goes up 5 every single time. You have to do this because every observance is not going to be exactly that. Good? Okay, what is the value of the correlation coefficient? Vocabulary. Vocabulary. What was correlation coefficient? R squared or R? I'll give you that. Okay, it was the R. Because this thing, coefficient of determination, tells you what percent of what is determined by which variable. So let's go with R. From our calculator, we saw that R's value is 0.95. And so let's put that interpretation, let's put that phrase. So we say that there is there is a strong positive, finish it out. Good, linear relationship between student population and let's see here, student population and quarterly sales. How about that next thing? How about that coefficient of determination? That's your R squared, and it's at 0.90. I'm going to give you a hint. We use that as a percentage. We start off by saying 90% of the something. Let's see what you can pull out. 90% of the... Very good. Very good. 90% of the variation. And you know, you might more easily think of it as change. So 90% of the change in quarterly sales is explained by, and there's actually 3 words that could, 3 phrases that could go here, and I've seen it all 3 ways, and so I want you to be aware there's some options of wording here. So 90% of the change in those quarterly sales are happening because of, or are explained by, here's choices, a model. Okay. That means your equation, your regression equation that you just found, your least squares regression line, okay? The other thing you could say is the change or the variation in student population. Or I have also seen it this way, although technically not as correct. I have also seen it where 90% of the change in quarterly sales is explained by the student pop. They just say straight up the student population instead of referencing the change in the student population, which is actually more technically correct. Okay, good. So let's think about this for a second in real world terms. So 90% of the change in the sales they get is explained because of the change that's happening in the student population. Okay? So that's like saying what's determining what. So question, use your brain and your business sense and tell me what could be attributing to that other 10% of sales changes? What's some other real world things that might be causing other sales changes? Oh, good. I like that. Very good. Economy, time of year. Economy, I heard time of year. other restaurants, other competition. Very good. Okay, so 10% of all the change in quarterly sales is attributed to those other variables. We don't know what, but something else is doing it too. All right, very good. Next, let's predict those quarterly sales for a population of 12,000 students. So what are you going to do with that? Plug it in. Very good. Let's predict. So our prediction for quarterly sales is 5 times 12 because it's in terms of 1,000 plus 60. So we get a prediction of 120,000. That's our predicted quarterly sales for 12,000 students in that local college. Okay, so we answered that. What is the residual? Here's another vocab word. First of all, what is residual? What does that mean? Good, that's correct. It is. So let's remember that the residual is that difference between what was observed and what was expected. So we know it as AP, actual minus predicted. Also, you could say observed minus expected. Where have we recently heard observed minus expected? In our chi-squareds, yes. That was our last chapter in our chi-squareds. Very good. Okay, so observed minus expected is how we want to do that. So let's talk about this. We've got expected is 120,000. Okay, that's what is on our prediction line. What's observed? What was observed at x equals 12? Where do you go to find that? Ah, very good. On the front, okay. So observed is 117,000. So our piece of data was close to 120,000, but it was 117. So our observed, okay, equals 117,000. So if I do observed minus expected, you need to go in that order. That gives me a negative 3,000, which tell me in words what that means. Good. What happened? In the reality that happened was 3,000 less than what was predicted. That's what this means. The reality is 3,000 less than predicted. Okay? So therefore, does this equation underpredict or overpredict at this particular point? Did our equation underpredict or overpredict? It overpredicted. Reality is less than the prediction, so the prediction overestimated. That's another way you're going to see that. Overestimated what actually happened. Okay. All right, now we're getting into more depth of understanding, because this is asking about a transformation. And we spent a whole month right before Christmas talking about why you have to transform and how you transform and all those calculator processes and flattening the curve and all that kind of stuff. So give me a brief synopsis of what this transformation stuff's about. Good. We see something, it's not linear, so we take it and we run it through a log or an exponential equation, quadratic. We could do those kind of things to flatten it out and make it linear and fit the data better. That's what we did. Remember, our power models would log the x and the y. Okay, so we'll revisit that in the upcoming month. But what could I do to see, do an analysis to see if my data needs to be transformed? I need to now get into some more specifics. What should I look at? Very good. You want to look at the residual plot. This, if it shows any pattern, then we're going to need to transform the data and flatten out the curve. So, how do we do that? Calculator steps. Again, that's have several here. So let's see. If I want to look at the residual plot, then I'm thinking I need to get the residuals first. Okay, let's start. Okay. So where do you want to put the residuals? Good. Let's put them in L3. So stat, edit, L3. Move your black cursor on top of the L3 to command it to compute the residuals. And where do I find that command? It is second stat. It used to be at number 7, but since I've been doing some chi-squared stuff, it's putting that contributor there. So, but if I go to number 8, ta-da, okay. Remember that's under your second stat. That's under your special lists there. Okay. So enter. So as you can see, I'm commanding L3 to compute the residuals, and this is the big mistake that happens. Ready? If you have not stat calced the line, if you haven't calculated the line, which we did a few minutes ago whenever we did ln reg AX plus B, if you hadn't calculated that line, your calculator could be thinking of some other line from like Christmas or whenever it was that we just relasted a line. You have to make sure that you have calculated the line of L1 and L2 before you do this, or else your calculator is not thinking of the correct prediction line. Did you all sweat cap this data, L1, L2? If so, then you are ready to do this. So here we go. Okay. And there are the data. Let's analyze here. Look. Oh, at the 12 mark, right there, at x equals 12, L2 was 117, which was a discrepancy of negative 3,000. We already did that in the computation. Okay, so let's look at it. So how do I look at it? Second stat plot, and second stat plot, and I look at L1 and what? L3. Very good. Okay. Zoom 9. Ta-da! There it is. So, talk to me about what we're seeing. I see no pattern. I see data located on either side of the line. Okay? The whole way. So to me it looks like that line in the middle goes through the data with things sprinkled on each side evenly. Okay, so we're going to kind of sketch that. So we go like this, and we label our axes. This x-axis was L1, and what data was that? Student population. This y-axis is was L3, and that was what? Good, the residuals of the quarterly sales. Okay. So it's the residuals of the quarterly sales. Okay, so here's a rough sketch. Okay. And we see nice even scatter across that. So, should the data be transformed? That's our question. Should the data be transformed? The answer is no. Why? Good. No pattern in residual plot implies that what? That the linear model is indeed appropriate. Good. Good, good, good. Okay. Hey, do you know what? This is kind of weird. This is brain stuff. But do you know that whenever you learn something, your brain kind of makes a little tunnel, an electrical impulse to like where that stores that data, so you can, you got the data, then you make this pattern, this electrical thing to retrieve it. Well, since we did this back in November, hopefully you dug those tunnels and made all those little connections to this data. Well, now that we're visiting it, hopefully every time you go back and visit it again, you strengthen those pathways. So we're just like cementing those tunnels and making them really strong so that we can easily retrieve all that information and put it all together. So that's why this review and coming back to this is so important. It's strengthening all that stuff that we had done back in November and December and such, and may have forgotten some of. All right. Last thing we want to do is be able to remember what's on a computer printout and what all these numbers mean. There's tons of them, tons of labels. This is a computer output of data relating X, which is the length of a steelhead trout in inches, to Y, which is the weight of the steelhead trout in pounds. Just generally speaking, do you think there's going to be a relationship between length of the trout and the weight of the trout? Yes. Okay. So according to this computer printout, where am I going to get the information for the regression equation? Not down here. Do you know that this analysis of variance is going to be used for the ANOVA test that they used in Moneyball, and we don't do that in this course? That would be like the next thing we would do after. So no, there. That's for multiple means. Okay, not going to use that. What do you think this word constant means versus this word length here? What are those two things representing? What? Your A and B values, yeah. So in our equation, one of them is our slope and one of them is our y-intercept. Okay. Now there's a whole row of numbers here. What in these whole row of numbers do I use? Good. Is coefficient. So, is the constant number, negative 19.342, representative of the slope or the y-intercept? It's the constant one. It is the y-intercept. Because the slope is usually right next to what? It's usually mx, which is your variable. And what's our x variable? Length. So this is your x variable, which is going to be related to that slope value. Good. Okay, so now in words, what's our regression equation? Predicted what? Good. And I'm going to put the intercept first. Question. Is this y-intercept a plausible number for a length of a 0 inch length trout? No. The length of a 0 inch trout is not going to weigh negative 19 pounds. So you need to know that frequently the y-intercept is not a plausible value. Okay? Y-intercept is frequently not plausible, and the reason is because that's typically extrapolation. Remember that word? Extrapolation occurs when, see, here is the weight. That's the length. Here's the weight. Okay, this negative 19 makes no sense. Because guess what? All our data was here. And this down here is far away from the observed data. So that's called extrapolation. when you're using something far away from the data. Okay, next, determine the value of the correlation coefficient. What is that? So what? R, good. Where do I get R on this thing? From the what? R squared, good. Here is R squared. They won't tell us R, they'll just tell us R squared. And by the way, R squared adjusted is none of your concern. That comes from knocking off the highest value and the lowest value of the sample. So they're kind of trying to account for any extra variation and knock that off. So, but we do not use that here. But that's where that comes from. Okay, so we got R squared. If R squared is 97.7%, then what will R be? Good. It's the square root of that. So the square root of 0.997 is 0.998. It's supposed to be 0.977. Okay. So that comes out to be 0.988, which is a strong positive linear relation. Oh, positive? Do I know it's positive when I square root? It could be negative. Can our correlation be positive or negative? How do you know if this value is positive or negative? The equation, what about the equation? The slope, very good. If it's a positive line, then you're going to have a correlation between 0 and 1 because it's positive. If it's a negative line, then you're going to have a correlation between 0 and negative 1. So you have a negative correlation. The sign of the correlation corresponds with the slope. So yes, since slope is positive, this is positive correlation. Good. And our last question here. What proportion of observed variation in weight can be explained by the regression equation? That's a big bunch of vocabulary right there, so let's say it again. What proportion of the variation in weight can be explained by the regression equation? Good. That is a statement about the definition of R squared. 97.7% of the variation in their weight is explained by the variation in their size, or their length. Okay? Very good. Okay, so that is technically the end of the regression review. Now we are going to go on to this next page, and I'm going to teach you two things from that. I want to stop right there for just a second.